Okay, so let's go ahead and import our geometry. We're working in CGS units, and I want this to be a diameter of 1. So let's go ahead and scale this volume. So now our diameter is 1. Also, you'll notice that some of these curves are kind of trimmed in parts, so we're going to regularize these curves, which show up in a few spots. And I'll compress our IDs. Next, we want to have a load surface here, so we're going to trim off these little legs. So to do that, we're going to first create a vertex at the center of this arc. And then we'll create arcs that trim each one of these little legs. Another thing we want is we want a surface around the outside to hold down our part, our spring. And so this should be maybe a little bit bigger. There we go. Okay, so next what we need to do is imprint these curves onto our volume. Again, we'll do this one at a time. And then we'll delete these the free curves. As well as that vertex. And we'll compress IDs. And then we're going to go ahead and save this model. And next what we're going to do is we're going to create our block that we want for this part. So we're just going to have one material, one block, call it the spring, and volume 1. Next what we're going to do is we're going to assign a meshing scheme. So we're going to do a sweep mesh. We're going to mesh this top surface and then sweep through. So we'll do a whole scheme here. And actually, first let's do let's mesh this outer one first. That's maybe a little bit too fine, so we'll delete the mesh. We will go all size. Let's see what 125 gets us just for a size. Yeah, that seems like a fair density here. So obviously that mesh is kind of, we want it to be a little bit more regularly shaped. So then we'll do a smooth using the Laplacian, all nodes, and we'll give it a tight tolerance here. Okay, so that's much better. The next thing we're going to do is we're going to mesh this inner surface. And we're going to also do this with a whole scheme. And now what we're going to do is we're going to say we want to have 4 radial intervals on this surface. And then we will also smooth this surface. So make sure that surface is selected, set tolerance, and apply. And then the last step we're going to do is we're going to mesh just this final surface. And we'll use a pave mesh for it. Okay, so that's what we'll use for our mesh. And again, we're not going to spend too much time trying to clean up some of these elements just in the sake of time, but we could if we want, but we're not going to spend that here. So what we need to do is, since we're going to apply a boundary condition on the displacements, so a Dirichlet boundary condition here, we're going to need to have a C0 continuity across this interface. So we need to put all of these edges into a group called CF crease entities. And so we're going to create group CF crease entities. And again, we could do this, I think, up through here. And so then what we just want is we would say, again, that we want all of the edges in this curve. That curve is 136. So we're just going to say, as opposed to using this, because I'm not completely sure, I'm more comfortable here with the text. We'll say group CF crease entities, add edge all in curve 136. And again, that's because we're going to apply this group in this creasing on the mesh entities, which are the edges of the quads here. All right. And then what we want to do, so we can just see up here that we've got this CF crease entities, which if we zoom in, we might be able to see that they're the edges, not here. The lighter green is actually the geometry entity. Okay, so next what we're going to do is we're going to create our side sets. So we'll say side set 1 is going to be called push surface. And we'll do face all in the surface. And so again, I just feel more comfortable doing this. Well, I suppose we can do it like this. Face all in surface. We just need to be able to select my surface. This is surface 46. And then side set 2, we're going to call it hold surface. And it will be all the faces in surface 48. And then right now Coreform does not support, or the Flex product does not support many to one. And so this is why it was important that we applied our side sets to faces and our group to edges, because we're going to create a composite surface out of these three surfaces. So we'll just select these three surfaces and keep the default settings. This will be virtual geometry or virtual topology. So what we'll note is that we still have our edges in that group, and we still have our faces for the side sets. And our block is still the volume, which we haven't yet done our volume mesh. I'm going to go ahead and again just save real quick. Next we're going to do is we're going to set up our volume mesh scheme. So we're going to mesh this volume. We'll specify that the source surface, so now again it's a composite single surface, and the target will be this lower surface. And then you'll note here, since I've used extrude most recently, this is the default scheme that we want to have. We don't want it to redistribute nodes on the bottom surface. We want this to essentially be an orthogonal projection. Okay, so now it's meshed our part. And we'll go ahead and again resave. And then we will use build uspline from mesh. Okay, so it is finished. To note that, so it gives out some information about what it's done, but notice this, the default was to have degree 2 with a continuity of 1. But this function, so I suppose we can show the syntax. This function will automatically keep this crease in here. And so across this crease, it'll be C0. Let's go ahead and just draw our U-spline. I'm not sure this will work in 3D. Yeah, so we can't do it for a 3D U-spline inside a trellis yet. But what has happened is our U-spline has been created as a simulation card. And from here, we're going to go ahead and build our input deck referring to these. Okay, so next what we're going to do is build our simulation. And as a quick note, so in the simulation card editor, these cards, when they're saved out to a simulation file, are saved out as JSON. And so what we're going to go ahead and do is we're going to import card deck that have materials information. And so here you can see I've got a card that's a finite deformation isotropic elastic plastic with logarithmic strains, and it calls off for it to have another card or like a sub card for yield surface properties, and that's defined here. So this is the ID of 1, and it's a perfectly plastic model, as there's no, as this value here is 0, and this is again CGS units. So we'll go ahead and import those cards. And so we can see that these cards have been imported. And I'll go ahead and give this a name. It looks like I forgot to include that in there. I'll call this okay. So next what we're going to do is we're going to add, so now instead of importing cards, we're going to go ahead and create cards manually. So we're going to go ahead and add a part. We'll call this the spring. Oh, yeah, we've not added yet a formulation. So one of the things that you can kind of notice is that in the card editor, there's a little warning sign saying you've not fully defined this part or this card, as well as there's some red items. I need to create a material formulation. So let's actually do this first. So formulation for a solid. It's a 3D solid, P+1 quadrature scheme using that material that we created. We'll call this plastic solid. So now on our part, we can use that formulation. And then we'll use the subdomain ID, was that, again, the spring. And everything here is now turned black, so it's good to go. For some reason, it looks like, oh, I forgot to hit apply. Now what we're going to go ahead and do is we'll add a time step card. And let's go ahead and use quasi-static with correctors. And we'll just leave the default settings here. Actually, so let's go ahead and let's set our max iteration 0 to 10. And then let's use line search. So next we're going to set up our problem and control model. So let's call this push spring. Actually, let's maybe call this spring fatigue. Let's use our part and that time step ID. And right now on Windows, there's really no options to choose from here. So we'll just leave these as the default to use super LU. Control model. Let's take a small initial time step. Let's do 10%. Let's go load it up to load of 1. Our control model. And we could choose to set adaptive time stepping here. Might come back later and choose to do that. I'm going to use just a fixed step size of 0.1. So now let's go ahead and one of the things we're going to need, a couple of things we're going to need are temporal functions. And so that we'll need later on. So I just know we're going to need these. So I'm going to make a constant temporal function. Make this one just called always and forever. It's just going to be value of 1 for essentially all time. And I'll create another one that's linear ramp 0 to 1. Zero, zero, time 1, function value is 1. And now what I'm going to do is I'm going to create my boundary condition. So apply displacement, velocity, acceleration to the nodes. So a nodal condition on these subdomains. On a nodal subdomain, we're going to apply dVA. And so we'll call this hold spring. This is going to be our hold surface. And then we want to hold it in X, Y, and Z. And use our always and forever temporal function. Oops. And it's a displacement type. And then X, what we'll go ahead and do is apply a scalar field load. And so we'll call this push surface on this subdomain. And then the load type is a pressure. And I just haven't done the math on this yet. So we're just going to pick a low, something that should be a low pressure in dynes. Let's just be safe and go with 1. Again, I've not really thought about this. And we'll say that that was defined in the reference configuration. And then this one will lamp linearly from 0 to 1. Hopefully this won't be too much of a deformation. If it is, we'll have to come back and change the values around. This may not be physical, but that's not my concern with this first pass of just trying to get a simulation to run. All right, next what we need to do is we've created these conditions, but we need to actually assign them to the problem. And so we'll specify which boundary conditions are active for our problem. And so the boundary condition that is active is hold the spring. And then for our field load, the active field load is push spring or push surface. All right, and now the last thing that we should need to do before we can run our simulation is define output. And we want output on spring. Let's maybe go for displacement. And then let's just see if we can even get displacement to work first. And let's say go for, since we know that we're going to spit everything out at every 0.1, let's just go for delta step of 1. And then spring results. And for the sampling type, we're going to use the new Bezier sampling that Coreform recently developed, which is in the VTK file type. And hit apply. We'll just look through, make sure that there's no, maybe, oh, yep, I did. Always and forever. So you saw how I was able to see that there is a little icon telling me that that was not working. Now we hit apply, everything's gone. So now what we're going to do is cross our fingers and, well, first let's go ahead and export this card list. And again, we could open this card list. And this is why, again, it's kind of handy to have things listed out here in cards, because as you can see, definitely we've got our geometry or mesh combined with our problem definition. And so this is quite a long input deck. And then, so what we're trying to do now is see if we can run. And so let's go ahead and call this OPS sim. So we found a little bug, and Coreform was able to go in and fix it, fix a little bug that we had on the Windows build for the Crunch solver. And so I've gone ahead and I verified that this problem will go ahead and run with no issues. But just for to make things a little bit more interesting, we're going to make a couple of changes. First change we're going to make is we're going to change the or increase the value of our load field to maybe be a little bit larger. 1 dyne is actually a pretty low pressure. And then we'll also add to our output field equivalent plastic strain, since that's what we care about for this fatigue analysis. So go ahead and hit apply. I think I might have failed to hit, nope, I got it there. Okay, so now we've again finished our card deck, and we'll go ahead and say to run, and we'll call this output file _4. And then now Crunch runs and it spits its log out to the command line interface. And so you can see now our problem is running. We'll just let this finish. You may have noticed that so as it's going through each step with its correctors, and then it's also at each step putting out a time report to let you know how much time was spent in each stage, and this is the total time. There are still a few bugs in their reporting of how much time was spent, because obviously you can't have something that was 645%. So there are a few issues here, but in general, we see that this problem solved in about 31 seconds. And if you take away the writing output time, then maybe it's about 30 seconds, and that's on a single core on my Surface Book laptop. Again, if you recall, so in our output, we had said that we're going to save out a file with the name Spring Results in a VTK format. So what we can do now is we can open up PairView 5, and version 5.8 is the production version of PairView that actually can recognize these Bezier cell formats. So we'll go ahead and we'll open, and we'll open up the PairView data file, or the .pvd. And again, we make sure that we have displacement and equivalent plastic strain loaded. And so unlike some codes, ParaView will automatically recognize displacement and automatically warp by the displacement. In our case, we need to actually apply a filter, be warp by vector. We can access it through this GUI icon or through filter and alphabetical and then warp by vector. And then we choose we want displacement to be the vector we're going to scale by. And we can go through each, through all the times, so we can actually see it at the last time. And again, we still have a really low pressure value, so we're not going to see much of a displacement. So we can just add some scale here. So, scale it by 100, scale it by 1,000, until we can see some appreciable deformation. Another factor of 10. So again, this is, deformation here is scaled by a factor of 10,000. And again, this is because this is just kind of a toy problem that we wanted to just throw together to show the overall workflow. But you can imagine that if we had applied a higher load, we'd see maybe a deformation that would be somewhat similar to this. Obviously, this would be a highly nonlinear deformation, and our real deformation is certainly appears to be within the elastic region or the linear region. So what we need to do is we can go ahead and change representation from this surface representation to have edges. So we can now see our finite element edges on here. And also we can go ahead and color by, say, the displacement. So again, our displacements down here are in centimeters, so this is a very small displacement, obviously. And also we can do, so you can notice that there is some fastening that's going on in ParaView. And this is where we can use the Bezier representation to get ourselves a more refined representation. So there's this nonlinear subdivision level. And so instead of one subdivision, so if we went to 0 subdivisions, everything would be linears, right? So these would be like linear elements. And then essentially as we subdivide, we're adding more triangles to capture curvature. And so we can take that up to say 4. And we can go higher up if we wanted. A few things that I have noticed are, this is a bit maybe in the technical details, but Coreform is having to, or is fitting the mesh elements to the geometry using a Bezier projection. And that implementation still seems to have a few kinks here and there, because obviously in our CAD model we wanted this to be a flat face. So there's still some improvement to be done, but that's not on the GUI side of things. That's going to be in the implementation side of things. And I do believe that that's on Coreform's roadmap to improve. And then again, what we cared about was equivalent plastic strain. And because we're in that linear regime, we see that there is no plastic strain, right? So our plastic strain here is 0. And so through the Coffin-Manson approach, we would not predict a low cycle fatigue. So what we can go ahead and do is let's maybe try increasing our field load by, say, a few orders of magnitude. So we'll go up to 10,000. Actually, let's go up to like 100,000 dynes. So this should be about a Newton or a Pascal, I believe. Let's change our output name to be maybe load 2. And we'll go ahead and rerun our simulation. We'll just call this OPS 5. And so Coreform creates a new tab. So we can still look at the old tab if we wanted to see our old simulation results. But here we're going to go ahead and run this new one. You can see now that we're definitely spending more time on our nonlinear iterations, or more nonlinear iterations to reach convergence. And we'll just let this finish. And so we can see is that now we've got a large enough load that our problem doesn't converge within the amount of nonlinear Newton iterations we've allowed for it. So we've gotten to about, I think we've completed time 0.6. Again, that's pseudo time, so it's a scaling of our load surface. So now let's go ahead and let's actually load in this case, spring load 2. And again, we can do all the same things where we're going to go ahead and use increase our subdivisions, and then we're going to warp by vector, and again warping by displacement. This time we'll use scale factor of 1. So here now we can see the displacement we've got at this stage, and we need to reset our nonlinear subdivisions. And so we might now be able to see some equivalent plastic strain. We plot that, and now we see some plastic strain that's developed in our model. This says we have some negative equivalent plastic strain, which, assuming that EPS is equivalent plastic strain, everything should be positive. Let's just see if we change our color map color scales. Okay, and so these strains are now on the scale that are valid for Kaufman-Manson, and at least they should be. Yeah, so well, I mean that. Yeah, so these should be accurate because they're within 10e minus 2 to 10e minus 5. So we should be able to use these results for prediction of low cycle fatigue via Kaufman-Manson. Now, one of the questions you might be asking is why did this analysis terminate so early? Again, that was because we only allowed for a fixed step. So we want this model to be able to take cutbacks if it's not able to converge on a certain time step. And that's where we can, in our problem model, where's this at? Oh, control model, here we go. So we could set an optimal, so maybe I want optimal to be, say, 5 iterations with the windowing of 2, growth factor 1.5, reduction factor of 0.5, with a minimum of 1e minus 2, and a maximum of 0.1. And we'll go ahead and rerun this analysis. And we'll let this one finish. Okay, so this one gets further due to our line stepping. It's still it's going to take too small of a step at time 0.74. So it does get a little bit further than our previous analysis had. But what I believe to be maybe possible little issue is that if you recall, I'll pull up this model again. We have some elements here that may themselves just not be very well behaved. So, personally, I'm a little concerned with some elements here, but let's just say that, we're running analysis. Maybe we want to try a different mesh, or we want to say increase the degree of our bases and change the mesh. And so let's just go ahead and take a look at how we might do that. So I'm going to go ahead and close these analysis out logs. Now, what I can do is I've gone ahead and made a copy of my last simulation file as a JSON. And if we open up this JSON file, what I'm going to do is I'm going to go ahead and remove all the portions of this JSON file that deal with the mesh. So I'm just going to go down to my simulation parameter settings. And we'll find the last okay, so we may have to, well, let's do this. Might be easier for us to just remove the cards from here. So I'll remove the basis U-spline. I'll keep these. I'll remove the part. I'll leave the part, but I'll remove the patch. And then I'll remove these subdomain definitions. Okay, so this should be just my cards that I had. And I think I also want this domain spline solid to be deleted. So these are just the cards that are like parameters for the setting. It's not the actual model. And so I could export this card list as my parameter JSON little file. So you see here, there's nothing here that talks about the mesh. Then I can do two things. But what I'm going to go ahead and do is I'm going to go ahead and as I save my trellis file, I'm just going to create a new model and then remove U-spline or U-spline remove. And now I'm going to go ahead and delete all of these cards. Go ahead and reopen my trellis file. And what we're going to need to do is we will need to reset some settings if I want to do a whole new mesh. But first, let's maybe just build U-spline from mesh. And we'll have the degree, maybe be degree 5 or 6, and continuity of 5. Let's not go too big. Let's go with P3C2. So this will be a cubic U-spline. Okay, so now we've built our U-spline. And actually, one of the things we notice is that the IDs here have continued to increment. So we're going to need to, since these won't match up with our cards that we've already created, we'll need to go ahead and actually start a new version of Trellis, or a new instance of Trellis to get it to kind of compress IDs. So there's no compress IDs functionality yet to really reduce these IDs that are counting up. So I'm going to go ahead and restart Trellis and we'll join back in. I probably need to be a bit more thorough because many of these cards are coming back in and then needing to have their subdomains reassigned to them. So here I'm reassigning the formulation for the part. what the subdomain is. So I'm just going to walk through each of these now and just make sure that everything has been updated. So we want to add the spring as this subdomain. We want to add back our push surface subdomain. I'll just go walk back through the other direction. Because I forgot to hit apply here. Okay, I believe I've fixed all of those types of errors. Yep, and this is exactly what I thought. I thought this would maybe elucidate that we got a negative Jacobian, so we probably have, again, this, um, my estimate here is that probably this element, I mean, just if you look at it, right, if it has to come in as a tangent, we're probably dealing with a poor Jacobian. And so we would need to go ahead and make just a whole, maybe a whole new mesh that maybe has a few better elements. But anyways, that's just overall just kind of like this workflow that I just thought I'd go over.